Okay, so we are starting unit 2.3 today, and we're going to finish 2.3 and 2.4, and then lesson 2.5 is the test. So hopefully we can finish unit 2 today. And so let me show you my screen, and we'll get rolling here. So again, today we're going to go over 2.2, or I'm sorry, 2.3. We're going to go over 2.4, and then 2.5 is the wrap up for this entire unit that we're going to go over as well. Okay, so to give you a breakdown as to what you have, obviously there's a quiz in 2.3, there's a quiz in 2.4, there's an extra credit practice and an extra credit discussion if you would like, right? Those are extra credit. And then you are only required to take the CST here, all right? So only the CST, not the practice and discussion are extra credit, and your CST is mandatory here. All right, and you have these, I guess, 3 lessons that you need to cover, or I would like you to cover, and bonus, benefit, whatever you want to call it. If you're able to do that, right, then you will have no homework from me in terms of pre-calc, okay? So the schedule we have set, you're going to have no homework for pre-calc this weekend. So again, hopefully that's a little bit of a relief there. So get these 3 units done today, and then you're done with pre-calc for the weekend until Monday. All right, but we got to get through those in class today right now. So moving forward here, all right, simple transformations of sinusoids, right? And remember, sinusoids are functions of sine and cosine. Right? How do we graph those? That's what we're talking about here. And now we're going to look at transformations of those, right? Moving those up, down, left, right, stretching, compressing, all of that stuff. All right. And hopefully, again, hopefully this is nothing too drastically different, especially the way that we ended with transformations of graphs in Algebra 2 for semester 1. Okay. But we'll refresh ourselves in case we weren't in Algebra 2, and we're also just, again, re-solidify that knowledge that we have. So in general here, I know this is maybe a little bit different than we're used to seeing it, okay, but in general, if we look at this, all right, our base function is this f of x here, all right, our base function is f of x, and as you can notice here, we have these other variables, a, b, c, and d, all right, and depending on what constants are there for A, B, C, and D, this is essentially how we stretch, compress, and shift all of our functions, right? In general, right? We either add it to the x directly, we add it at the end of the entire function, right? Do we multiply the x directly, or do we multiply the entire function, right? Those are basically the 4 things that we did to transform any function here, all right? But again, it might look a little confusing, so let's break it down even simpler. So in general here, to understand the effect that each of those constants have, or to figure out if I put a constant somewhere in my function, how is it going to change my graph? Okay, so there's basically 5 questions here. Did the zeros change? Did the max or the min values change? Did the period change? And did the amplitude change? Right, and amplitude is a new word for us in math, but it should be a familiar word for you that we used in chemistry class. Right, so amplitude, again, being the height of the wave, right, the height of the wave. So if we look at this, again, our zeros, where it crosses the x-axis. Our max value is the absolute top, right, our peaks, our max value. Our min value is the lowest part, right, our valleys. Period is how long it takes us to get back to our original point, right? I start at this 0 point, I go up, I go down, I come back to where I started, right? Because I'm going to go back up again. So a period is how long it takes me to get back to my original location. All right, and then the last one there again is amplitude, right? The amplitude, the height of the wave, right? The height of the wave. So max value is the peak. The top value, min value is the lowest, and then the amplitude is the size of the wave. All right, the size of the wave. All right. So if we look here, okay, we started with this a little bit yesterday. Okay, we started with this, but if we look here, we have sine of x versus 3 sine of x. Okay, sine of x versus 3 sine of x. So if we look at our function here, what happens when we multiply our entire function by a constant? Okay, so if we look here, if we look, right, the black is our original. It's our original sine function, right? It starts at 0, goes up to 1, comes back down to -1, right? And it's got a period of 2 pi. It's got a period of 2 pi. So then we're going to look at, okay, what happens when I multiply by my constant? All right, did it change the zeros? Did it change those values? Did anything else change? Right, so if we examine this, first question, did our zeros change? Okay, the answer is no, they're still located at multiples of pi, right? Every time there's a pi, 2 pi, 3 pi, right, we're going to have a 0 there. So no, that didn't change. Did our max value change? Well, the answer is yes, right? We now have a maximum value of 3. All right, and same way, we have a minimum value now of -3, right? So our max and our min values did change. Did our period change? No, it's still 2 pi, right? To complete an entire cycle, it's still 2 pi. And then the last question, did our amplitude change? Yes, okay, our amplitude, instead of being an amplitude of 1 or having a magnitude of 1, it's now a magnitude of 3, right? So in general here, we changed our max and our min values, and we changed our amplitude just by multiplying our expression by a constant. All right, so given what we've seen, right, think about how would you describe it being multiplied by a constant? All right, so what would being multiplied by a constant look like? All right, and as we just found out, right, if I multiply by a number greater than 1, it's going to have this resulting increase, right? It's going to have this increase. It's shifting up. But if I multiply by something between 1 and 0, right? So maybe 1/2, we're going to notice that we have a shrinking, or we have a compression, right? Same thing with 1/3. I have a compression, right? So greater than 1 is going to result in a stretching. Less than 1 is going to result in a compression. Right, so right there, for y equals a sine of x, right? So if we multiply our sine of x function by a, if it is a positive constant, okay, it's either going to have a stretching or a contraction. So we're either going to stretch or we're going to shrink, okay? And if we are greater than 1, we're going to have a stretch. If we're between 1 and 0, we're going to have a shrink, right? Stretch, shrink. And regardless of if it's a stretch or a shrink, right, whatever that constant is, that constant now becomes our new amplitude. That constant now becomes our new amplitude. Right? So then, is it going to be the same thing for cosine? All right, and hopefully you're already saying it in your head. Yeah, duh, right? Duh. Okay, it's going to follow the same patterns. If I have a number between 1 and, or sorry, a number greater than 1, it's going to be a stretch, right? And see here, this blue line, 4 cosine of x. Well, my new amplitude is now 4. All right? And on the other side of that, if it's between 0 and 1, right, my 1/2 and my 1/4, that's going to be a compression. It's going to be a compression, and my amplitude, again, is going to be whatever that constant value is out in front. So then here, to just summarize here, okay, we can stretch or compress a function, one of our sinusoidal functions, by multiplying it by a constant. all right, by multiplying it by a constant. And if it's greater than 1, it's going to have a stretch. If it's between 1 and 0, it's going to have a shrink or a compression, right? So greater than 1 is going to stretch it. Between 1 and 0 is going to shrink it. All right, and what that's going to do is that's going to change the amplitude of our graph, right? The size of each of those waves is going to either stretch or shrink to the value of our constant. Okay, and the last thing I'll notice here is, or mention, is that if we have no other transformations on our functions, we don't shift it up or down or whatever, okay, that will also change the max and min values of our graph. Okay, that will also change the max and min values of our graph. All right, now here if we do adding a constant, right? So originally we multiplied by our entire function by a constant. Now we're just going to add a constant to our entire function. So I want to be really careful. This is sine of x and then plus 2, right? Sine of x plus 2. This is not sine of parentheses x plus 2. It's the function sine of x, and then I'm going to add 2 to it, right? That's the difference in the power of parentheses, okay? So now here, if we look at what happens when we add a constant. So now we're not just sine of x, we're sine of x plus 2. Okay, so hopefully you noticed that it moved the graph up by 2, right? Hopefully, again, some things are sounding familiar to what we already talked about with basic graph transformations here. All right, so if we look though, okay, did plus 2, did adding that 2 change our zeros? Well, yeah, it did. It moved our entire graph, so now we have no zeros, right? We have no zeros. Okay, did it change our max or min values? Absolutely, right? It moved both of those values got increased by 2, right? Our original max value was 1, now it's 3. Our original min value was -1, now it's +1. Right, so it changed our max and our min values. All right, the period, okay, the period is still the same. The period is still the same. All right, it still takes 2 pi to get back to where it started. Right, it still takes 2 pi to get back to where it started. And again, you could have chosen any points. They chose where our zeros normally are at -pi and pi, but you could have also chosen this -pi/2 to 3 pi over 2, right? As long as you know that when I subtract these, it's still 2 pi. That's all that matters, right? But it's still a period of 2 pi. It takes 2 pi to complete an entire cycle. And then looking at the amplitude. Okay, our amplitude is untouched, right? If I look from the middle point to the peak or the middle point to the valley, it's still a value of 1. So no, my amplitude has not changed, okay? And my amplitude has not changed. So it looks like I've just taken my entire graph and moved it up 2 units. Hopefully that sounds familiar here. All right, so if I was looking at y equals sine of x plus or minus d, right? Plus or minus d, depending on if d is a positive or negative value, that's going to tell us how we're going to shift our graph, either up or down. So again, as we talked about, if I have a plus value, I'm going to shift up. All right, and then as you can bet here, if I have a minus value, I'm going to shift down. All right, and again, this could have been plus 1/2. It still shifted up by 1/2. This could be -5. It'd be minus down, right? Doesn't matter what the value is. Okay, it depends on the sign, right? If it's a positive value, we go up. If it's a negative value, we shift down. And hopefully you can notice here too that when we have this green one here, okay, we still have zeros, right? So shifting a graph up or down doesn't necessarily automatically mean that we don't have zeros anymore, okay? This just so happens that it shifted down and there are still 0 values. Okay, so paying attention to, it's not automatic that we're getting rid of the zeros. All right, so again, in conclusion, if I have a plus at the end, right, if it's sine of x plus a value, that's going to go up. If it's sine of x minus a value, it's going to go down. All right, and then as you can probably guess, it's going to be the same thing for cosine. Plus 2 goes up 2. Plus 1/3, I'm up by a value of 1/3. Minus 1/3, down by that value. Minus 2, down by 2. All right, so again, it is just taking the graph as is and shifting up or down. All right, so again, our summary of this is that if I see sine of x plus or minus a constant, right, that's telling you how the graph is going to shift. Positive means up, negative means down. Positive means up, negative means down. All right, so then here, if we go to our practice problems, the amplitude of the function 6x is equal to, all right, the amplitude of the function 6x is equal to, well, remember, we said that the amplitude now becomes whatever this value is, because this is going to have an effect of stretching my graph, right? And I can check that. And again, something I'll hopefully be able to point out to you is that what I'll be able to point out to you is that you can always go back and plug these into your graphing calculator. Okay, you can always plug these back into your graphing calculator. So if I share my desktop with you guys, all right, look, all you have to do, if you're confused, all you have to do is plug into your graphing calculator. All right, so I plugged in, I've got sine of x is in red. Oh, I didn't mean to move that. All right, I got sine of x in red, and then I typed in 6 sine of x just to see what it would do, right? Just in case I was confused or concerned. All right, and clearly it stretches my graph here to this new value. So my amplitude is 6. All right, so then moving forward here, what's the amplitude of this function? All right, so it's got a bunch of things here. 0.64 cosine of x plus 4, but it's only asking me about the amplitude. So what's my wave size going to be? Sorry, that's supposed to be 0.64. Right, it's going to be whatever my constant is out front here. All right, now if I look, the graph of sine of x minus 3 is my graph of sine of x, and it's going to be shifted down because it's a negative sign, and it's going to be down on the y-axis, right? Down on the y-axis. Because I'm adding to the entire thing. So it's down on the y-axis. Okay, so then if I look at the function, it says choose the function that's represented by the graph in red. All right, so my black one here is my parent function. All right, and if it starts at 0, that means we're dealing with a sine function. Okay, it starts at 0. We're dealing with a sine function. It's not shifted up or down. It looks like it's just compressed. It's compressed. And if we look here, this is divided into thirds. So this is 1/3, 2/3, 3/3. Okay, so it looks like it's compressed down to an amplitude of 1/3, which means that my value here has to be 1/3 sine of x. It has to be 1/3 sine of x there. All right. If I look at this guy here, all right, my parent function is here in black. My parent function is here in black. So again, I'm still dealing with a sine function because it's starting at 0. It's asking me, what's my y-intercept? Okay, well, that's where it crosses the y-axis. That's talking about 2. All right, what's my amplitude? Well, going from 2 to 5 or 2 to -1. Regardless, my amplitude is a value of 3. Okay, my amplitude's a value of 3. So if I look here, I know that I have a factor of 3, and I moved my graph up 2. Okay, so I have a factor of 3, which means it's going to be 3 sine of x. It's going to be 3 sine of x. And since I moved up by 2 values, it's going to be sine of x plus 2. 3 sine of x plus 2. Okay. All right. So again, hopefully you're noticing some familiarities here. All right. But regardless, okay, when I'm adding or multiplying the function itself, right? I'm not dealing with x, I'm dealing with the entire function. Okay, that's when I'm going to be dealing with moving along my y-axis, my stretching, my compressing on the y-axis, moving up and down, all of that stuff. All right, so when I'm dealing with directly impacting the output value, I'm talking about my y-axis. All right, but now we're going to look at something that might be a little bit different. Okay, it's going to be similar, maybe a little different. Is stretching and shifting in the domain. So looking at our domain values. Okay, looking at our domain values, right? Our x values here. Okay, so we have 2 ways that we can really modify x. We can look at x and we can multiply it by a constant, right? Or we can look at x and we can add a value to it, right? So again, this is where we actually go in and we add it directly to the x, and then we carry out our function, right? So we, instead of writing x by itself, we would write x plus c, right? That's what this is saying. So instead of saying f of x, we would write, everywhere we see x, we would write b parentheses x plus c, right? We would write b parentheses x plus c. All right, again, assuming that b and c are both positive constants here. All right, so if we can remember what happens when we multiply, right, we're going to be looking at stretching or compressing. So again, instead of having the 2 out in front, instead of saying 2 sine of x, we're saying now sine of 2x, sine of 2x. All right, so what we're going to do here is we're going to stretch and compress this function in our x direction. So if we look here, that's our normal sine function. When I wrote 2x here, okay, when I write 2x here, it looks like we've squished our graph in the x direction. So now multiplying by 2, looks like I've taken this graph and squished it in, right? I've made it go faster, effectively, right? So if we look here at all the questions, did our zeros change? Well, yeah, absolutely. Now instead of being at every pi unit, it's every pi over 2. It's every pi over 2. All right. Did our max values change? No, they didn't. Did our min values change? No. Okay, that means our amplitude didn't change. The only other thing that changed is our period, right? Instead of being 2 pi, it's now just 1 pi. Instead of being 2 pi, it's 1 pi. All right, and our amplitude changed by dividing by whatever that constant was. So we had 2 pi originally, and we divided it by this constant out in front. So 2 pi divided by 2 gives us our 1 pi, right? So that's how we changed our period there. All right, so again, if we're looking at 2x or 3x, right? We're talking about making our graphs go much faster, right? If we look at something like 1/2 x, we're going to stretch our graph out, effectively make that period longer. Same thing, 1/3, stretch that graph out. So that's what the difference would be. If I'm multiplying by a number greater than 1, it's going to have an increase on my, it's going to have an increase on the number of waves I have, right? Or it's going to shrink my period. If I have a number between 0 and 1, it's going to elongate the period of the graph, right? How long it takes to get back to that original point. So again, greater than 1, it's going to stretch, it's going to shrink the graph here. It's going to shrink or compress our graph, all right? And what it does, again, is it shrinks the period. Okay, it shrinks the period. If I have a number between 1 and 0, what it's going to do is it's going to stretch the graph. It's going to take it and pull our graph out. It's going to elongate our graph. All right, and what it's going to do is when it elongates the graph, it also increases our period of the graph. All right, and if you look here, in other words, the period of our graph, right? The period of sine of x is equal to 1 over our value, it's equal to 2 pi, right? Our normal period divided by b, right? So again, if I go back to here, right, the period for this graph will now be 2 pi divided by 3. 2 pi divided by 3. So that will be 2/3 pi. So every 2/3 pi, I'm going to get back to my original. It's going to be much, much faster. Versus here, if I have 1/2, right, I'm going to have 2 pi divided by 1/2, which is going to end up with a period of 4 pi, which is why this graph, again, gets stretched out. Okay, so again, it's going to be helpful. You have to divide by our constant in order to get our new period. All right, and then of course, yes, cosine will behave in the same way. If I have a number greater than 1, it's going to shrink. And if I have a number between 1 and 0, it's going to stretch. Right, and it will have the same effect on the periods as well. So again, instead of having a period of, for 1/2 here, instead of having a period of 2 pi, it's going to have a period of 2 pi divided by 1/2, which is 4 pi. And effectively, look, that's where we get to. We get to 4 pi. All right, this guy, again, it would be 2 pi divided by 2. So that means I'm going to have a period of every pi. Right? So look here. I repeat, every pi units. Okay? So again, in the case of having constant b, where it's actually directly impacting our x value, if b is greater than 1, it causes a contraction or shrinking in our x direction. Okay? If it's greater than 1, it causes that shrinking. All right? If it's between 0 and 1, it causes a stretching, right? A horizontal stretching along our x-axis. And regardless of if it's stretching or shrinking, okay, we're going to divide by that constant of b. We divide by that constant of b, and that will give us our new period, right? How long it will take to get back to that original point. All right, and then I believe this is the final one here, shifting along our x-axis. Okay, shifting along our x-axis. So again, now we're going to go back to adding and subtracting when we're talking about shifts. And since we're dealing with our x direction, we're going to be actually directly impacting our x value here, right? So again, we're going to be dealing with adding and subtracting, all right? Adding and subtracting. So if I have my normal, and then I have x minus pi over 3. I'm going to shift by a factor of pi over 3. So let's see what happens. All right, I have my normal function, and then I'm going to shift by a factor of pi over 3. All right, I know it's hard to see here, but look, I've shifted to the right. I've shifted to the right by a unit of pi over 3, right? I've shifted pi over 3. So did the zeros change? Yes, absolutely, they're different. They shifted over by a unit of pi over 3. Did our max values change? Nope. Did our min values change? Nope. Did our amplitude change? Nope. Did our period change? Nope. All right, but we'll still go through it, right? Our min values didn't change. All right. The period is still the same, and our amplitude is still the same. All right. The only thing we did here was we moved along our x-axis. We moved along our x-axis. So again, given what we know, given what we think should happen, okay, the question is what happens if I add or subtract, again, that value, that constant value from x, all right? And again, if I subtract, I'm gonna move to the right, all right? And this one is subtracting pi over 3. This one is adding pi over 3, so I'm gonna shift to the left, all right? And this is the one where maybe a little tricky at first, but we just got to remember that when I add directly to my x, I'm shifting to the left, and when I subtract, I'm shifting to my right. All right. So again, in conclusion, if I'm adding, I'm shifting to the left. If I'm subtracting, I'm shifting to the right. Add, left, shift, subtract, shift, right. Okay. And then again, as you can believe it, cosine's gonna do in the exact same fashion. So if I add, I'm gonna shift to the left, and if I subtract, I'm gonna shift to the right. All right. So I can do either of those two functions there. Okay, so then here, summarize it. Again, hopefully not too difficult, but if I add c to x directly, I'm going to shift to the left, and if I subtract c from x directly, I'm going to shift to the right. All right, so then looking here at our practice, the period of the function. Okay, so again, this is where I'm going to take my constant value and divide 2 pi by it. So 2 pi divided by 1 over 4 is 8 pi, right? 2 pi divided by 1 over 4 is like saying 2 pi divided by 0.25. That's going to give me a value of 8. Period of the function 2 pi x minus 2. All right, so now instead of having this value of 1 over 4, I have this value of 2 pi. All right, so what I'm going to do is I'm going to take my normal period of 2 pi, and I'm going to divide by this new b value of 2 pi. So I'm going to be left with a period of 1. We'll be left with a period of 1. All right. Then here, if I have y equals sine of x minus 3, it represents that the graph should be shifted to the right along the x-axis. All right, it's to the right because it's subtracting, and we're moving along the x-axis. All right, looking at our red function here. Okay, if black is our original, we're starting at 0, so we know it's a sine function. All right, we know it's a sine function. The amplitude hasn't changed. Okay, so the amplitude hasn't changed, so we're not dealing with anything in the y direction there. All right, and we have now increased our graph. Right, our graph has been stretched. Our graph has been stretched. So we're now dealing with something between the values of 0 and 1, right? So we're going to multiply either by our 1/3 or our 1/2, right? So we're looking at these two here, right? And sorry, apparently I clicked it. Let's try again. But all right, so we've narrowed it down to these two because we know that it's a stretch. Okay, we know it's a a horizontal stretch. So then the question becomes, how would I get out to a unit of of 6 pi here, right? Instead of being at 2 pi where I normally am to get back to my original, I have to go all the way out to 6 pi, right? So the question becomes, is 2 pi divided by what number would give me 6 pi, right? And that number is going to be 1/3. It's going to be 1/3, right? So again, look here. If I know that my period is 6 pi, it's got to be 6 pi equals 2 pi divided by b, right? And so b is going to give me this 1/3. All right, and that's how I get to my final equation here. All right, so then again, if I look, this black line is my original here. This black line is my original. And it's asking me, it says, the red graph passes through the point -1. Looks like -1, 0. I know it's a little bit off here, but go with it. -1, 0. All right. What is the period of the sinusoid represented by the red graph? All right. So if I start here, how long does it take me to get back? How long does it take me to get back? Is the question here. And I don't particularly like this question because they didn't do a really good job of showing you what the period of the graph is. But basically what I would look for here is I would look for the point here or any point, right? I would look for wherever it comes back to completion. Wherever it comes back to completion. So if I'm looking here, for me, it passes kind of between whatever this 1/pi unit is. It's 1/pi unit. All right. Or you can see here, if I start here, I go 1, 2. So between -1 and sine of x, that's my period. All right. That would be my period. So let's see what happens if I type in 1 pi. All right. The answer is 1 pi. Okay. And again, I don't like that they used this this scale here. All right. I don't like that they used this scale. It's not very obvious. All right. But what I was able to figure out is that, okay, I'm sine of x -1. All right. So sine of x plus 1 is my period. All right. Or my period for 2 of these. So that's 2 times my period. So then I could just divide it in half. All right, I could divide that in half. Again, I don't like the scale they use, so I apologize. All right, choose the function represented by the graph. Okay, choose the function represented by the graph. Well, first off, we know that there is a horizontal compression, and we know that there is a shift in the graph, right? And we are able to look and see here that our new period is 1 pi. Okay, our new period is 1 pi there. So since it's 1 pi, we're able to know that our value we need to multiply is going to be a 2, right? So we're stuck between one of these first ones here. We know that we have to multiply by a value of 2. All right. Then our next thing is that we shifted, and we shifted back by 1 unit. Look, we shifted back by 1 unit. All right, and so if we shift to the left, that means we have to add 1. We have to add 1. So our final answer is going to be this 2x plus 1. All right, and again, they explain exactly what I said. All right, so if we know that the graph of the cycle is between, this is why I don't like the way that they did this, but this is apparently pi minus 1. So that point apparently is pi minus 1. All right, it looked like a pi to the power of -1. But basically what they were saying is If this is pi minus 1 and this is minus 1, then pi minus 1 gives me pi, right? They show that right there. So the difference between that is pi. So apologies that it looked like that was to the power of -1. All right. And then finally here, since the period is now equal to pi, right? 2 pi divided by b, so b must equal 2, right? Because we only have 1 pi as our answer. All right. All right, so then flipping and multiplying by a negative constant, okay? Negative constants, hopefully this is, again, very, very familiar here. But what happens if we let A or B be negative? Okay, we're gonna talk about flipping across our different axes, our X and our Y axes, right? They're just simple reflections here.
Start with the equation y equals sine of x. To reflect across the y-axis, you must graph the function y equals sine of -x. One way to visualize the reflected graph is to color the graph of sine as follows. Then reflect those colored pieces across the vertical axis. Here's the reflected graph. To reflect y equals sine of x across the x-axis, you must graph the function y equals negative sine of x. One way to visualize the reflected graph is to color the graph of sine as follows. Then reflect those colored pieces across the horizontal axis. Here is the reflected graph. The exact same thing will work for the cosine function. Start with the equation y equals cosine of x. To reflect across the y-axis, you must graph the function y equals cosine of -x. One way to visualize the reflected graph is to color the graph of cosine as follows. Then reflect those colored pieces across the vertical axis. Here's the reflected graph. To reflect y equals cosine of x across the x-axis, you must graph the function y equals negative cosine of x. One way to visualize the reflected graph is to color the graph of cosine as follows. Then reflect those colored pieces across the horizontal axis. Here's the reflected graph. You may have noticed that for the function sine, you get the same graph no matter if you reflect across the x or the y-axis. This is no surprise, since the sine function is odd. You may have noticed that for the function cosine, reflection across the y-axis does not change the graph. This is no surprise, since the cosine function is even.
All right, so we'll digest that a little bit more here on the next couple of slides. But again, I'm trying to show you guys what this would look like on a graphing calculator here. So if I were to just digest that a little bit more, all right, so we have f of x is equal to sine of x. Oh gosh. All right, sorry about that. Oh gosh. All right, so I have f of x is sine of x. All right, so that's my original function in blue. If I were to type in negative sine of x, all right, notice, okay, it is it is reflected. It is reflected across one of our axes. All right, it's reflected across one of our axes. And if I type in instead sine of negative x, hopefully you notice that negative sine of x and sine of negative x are going to be the same thing. All right, one is reflecting across the x-axis and one is reflecting across the y-axis. All right, but essentially, if we have no other transformations, they do the same thing. All right, if I look at cosine, if I look at cosine of x, goodness gracious, there we go. All right, so if I look at cosine of x in blue, if I look at cosine of x in blue versus minus cosine or negative cosine of x. All right, I've got cosine of x in black, and I've got negative cosine of x in blue. All right. This one's a lot easier to see that my negative cosine of x is reflected across my x-axis. All right. But if I type in cosine of negative x, right, that should reflect across my y-axis. But notice it looks exactly the same as my original function. Okay, so that's what she was trying to say in the video. All right, is that cosine of x and sine of x, when you do the reflections, if you're just transforming one of the parent functions, depending on if it's an odd or even function, it will end up looking the same. It could end up potentially looking the same depending on the transformation that you do. All right, but again, when in doubt, graphic calculator, always. When in doubt, look at your graphing calculator. All right. So again here, just to do some basics, okay, again, if we have it added to the outside, we're gonna shift up, right? We're gonna shift our function up. If we have it inside the function, we're gonna shift to the right. I'm sorry, shift to the right or to the left. Since this is added, we're gonna shift our function to the left. Okay, we're gonna shift our function to the left by 2 units. All right, if we have it inside the parentheses, that means we're going to stretch or compress in the x direction. All right, and if it's outside the parentheses, we're gonna stretch or compress in the y direction. All right, we're gonna stretch or compress in the y direction. All right. Same thing is going to happen with cosine. Same thing's going to happen with cosine. All right. But the only difference here being now in these new ones, we have the negative signs here. All right. So we have the negative signs. All right. So first off, again, you've got to figure out, am I going to stretch or compress in the vertical or the horizontal? All right, am I going to stretch or compress in the vertical or the horizontal? So if we look here, first off, let's start with maybe sine. Okay, so sine, since it's the only sine function. Sine would normally start at 0. Okay, it would normally start at 0. And it would, apologies. It would start at 0. Okay, so the only function that's starting at 0 right now is this value. Okay, so it's starting at 0, and we're multiplying that by a negative 2x. And we're multiplying it by negative 2. So this one gets reflected across our y-axis, right? It gets reflected across the y-axis, and we have a horizontal compression. All right, so again, the negative 2x, the negative value makes it flip across our y-axis, and since it's a positive 2, since it's a 2, which is larger than 1, it makes it a shrinking. All right. For the next one here, I have negative 1/2 of cosine of x. All right, well, this is going to be a compression. It's going to be a compression, all right, in the y direction. All right, it's going to be a compression in the y direction, and I have a negative value here, so it flips across my x-axis. It flips across my x-axis. All right, and then finally here, these would flip across my, this would flip across my y-axis. All right, and one of them would flip across my x-axis. All right, and then again, this one's going to be a stretch, a compression in the horizontal. This is going to be a stretch in the vertical. All right, so this one's going to be my stretch in the vertical. In addition to being flipped across my x-axis, this one here is going to be flipped across my y-axis. But it doesn't matter since it's an even function. It looks the same. It just looks as though it's the 2 function that's affecting it. All right. Again, I know that these can get a little bit difficult, especially with the pictures, but try to pick out the general trends here that you're looking for. Okay. So taking a look at our study guide here. Again, it's going to be all about these 5 questions, looking at how the zeros, the maximum, the period, and the amplitude change. All right, and then knowing, again, appropriate stretches, compressions that we have in the horizontal and the vertical direction, and then looking at our shifts in the X and the Y. All right, and then, of course, finally is is if we have a negative constant, all right? If we have a negative constant. So let me see, I'm trying to find where those are. Right, right here. Okay, so to reflect across the y-axis, you'll have negative x. All right, so again, to flip across our y-axis, you would multiply by negative inside. And if you want to flip across the x-axis, you'll multiply the negative on the outside. All right, same thing for the cosine function. And this is that last part of the video that woman was talking about that I tried to explain to you. All right, for the function y equals sine of x, you get the same graph, whether you reflect across the x or the y axes for sine. Okay, you'll get the same graph because the function is odd, right? So again, it will flip. But regardless of if I flip across the x or I flip across the y, these 2 graphs here will be the same. All right, they're not the same as sine of x, but if you flip across the x or the y axes, it'll have the same impact. All right, because it is an odd function. But for an even function, only if you reflect across the y axes, it doesn't change. Only if you reflect across the y-axis does it not change. Okay. Let me move this. There we go. Okay, so then, of course, you have a checkup here, but for the sake of time, I'm going to, again, fly through this and give you some helpful hints here. Okay, so when you're doing this, again, pay attention to, it's just basic transformations. All right, it's basic transformations. Understanding those rules of compression, stretching, and shifting is going to be really, really important to you. All right. And then paying attention to the difference between sine of x minus 3 and then the parentheses inside, right? So again, one is going to be a shift in the in the vertical direction, right? So this is going to go up or down, and this one's going to go left or right. Okay, it's going to go left or right. All right, and that's all I believe that, yep, perfect. That's all this is asking you to do, is to be able to look at the different graphs here. All right, and if we look here, at this final question, I wanted you to notice. So if we were to, it says, sketch the graphs of sine of x and cosine of x minus pi over 2 on the same axes. Okay, what can you conclude from this? The graphs are going to end up being the same. Okay, the graphs are going to end up being the same, because the difference between sine of x and cosine of x is just where they originally start. Right? Where they originally start. So if we can look at it, we can just shift them and they're the same graph. All right, because again, cosine of x normally starts at 1. Normally starts at 1. So if you notice, it's just an offset by this pi over 2 factor. So those are actually the same graph. Those could actually be the same graph. All right, so that's just a fun little thing there, right? They're the same, except for they're just offset a little bit by that pi over 2 factor. All right, so that's simple transformations of sinusoids. And again, reminder, you have that one quiz there. All right, for 2.4, we're going to talk about general transformations of periodic graphs, right? Graphs that have these trends that are repeating. Okay, graphs that are repeating. So we're putting it all together here, of course. All right, so again, reminders, A and D affected the vertical direction, B and C affected the horizontal direction, okay? And it says pay close attention to the constants C and D, right? They determine what's called the sinusoidal axis, right? And if we look at this new definition here, it's the axis of symmetry of the general sinusoid determined by the vertical or horizontal phase shifts. All right, so what that's talking about here is, sorry, again, the axis of symmetry. All right, axis of symmetry. So where it's going to look like a reflection, okay? Where it's going to look like a reflection. In normal, our normal one, it's reflected across the x and the y axes at perfect, x equals 0, y equals 0. But when we start shifting them around, it's going to shift where we can do our where it would look like a reflection. So for example here, if I have plus D minus C, all right, I'm going to be in this upper quadrant because I've added D, right? I went up D and I subtracted C, so I moved 1 to the right. I moved 1 to the right. And as you can notice here, this gray line in the middle, right? This gray line in the middle and this gray line vertical. Okay, this is now my sinusoidal axis. Okay, my sinusoidal axis. Because if I look here, this horizontal gray line, I'm able to look at my amplitude. I'm able to perfectly look at my amplitude A, right? It's got to be the same in the positive and the downwards direction. All right. And if I look at my vertical line here, again, this is where I could do my reflections, or this is where it has that periodic nature, right? So again, looking at this sine function, this would be our new sinusoidal axes. If I subtract C, subtract D, same thing, my axis has moved down and to the right, and I still have my axes there. If I add C, add B, right, I move left but up, so does my axes. And if I moved down and left, okay, so does my axes. It moves with it. All right. So now if we can look here at, graphing those transformed sinusoids. All right. We'll have to, perfect, as what they're saying. Okay, you have to first determine what the axis is going to be. All right. You have to first determine what is the axis. Is there a change to the amplitude? And then what about the period? Right? Those are our 3 major questions, and we can then sketch pretty much any sinusoid. All right, so first off, looking here, sketch the graph given of 3 sine of 1/2 x minus pi plus 5, right? A big complicated one here. So the first question is of course, looking at the different transformations. Okay, so I can notice here that I transformed all directions. Okay, I moved up, or I shifted horizontally, I shifted vertically, I have a stretch, and I have a stretch or compression in the horizontal. All right, so if I look here, all right, my axes has moved to the right by a factor of pi, right? I move to the right by a factor of pi, and I move up by a factor of 5. Because again, pi was my C value and 5 was my D value. So I moved over and up. All right, so now I've determined my new axes. I've determined my new sinusoidal axes. All right, so that is super helpful to draw that on there. All right, so then the question is what is my amplitude? What is my amplitude going to be? Well, my amplitude is going to be that 3 value, right? Because I have 3 sine of. So my amplitude is now 3. Okay, so then if you've noticed here, they're able to draw that dashed line for my amplitude. So based on my axes, I'm going to be up 3 or down 3. That's the max that I'm going to go there. All right. Then the next question is going to be, what is the period of the sinusoid? How often is it going to repeat? Right? Sine is normally 2 pi. Right? It's normally 2 pi. But in order to get my new one, I have to do 2 pi divided by b. Right, which is this 1/2 value. So my period is going to be 4 pi. My period is going to be 4 pi. So if I look at my axes here, if I start at pi, I have to repeat every 4 pi's. So it's going to repeat at this 5 pi unit. This 5 pi unit. All right. Okay, there where it's repeating. All right. And I can do the same thing in the negative direction. All right, I go back 1 pi and then 3 more pi's. So I would repeat here back at this negative 3 pi. All right. Perfect. Back to the negative 3 pi. All right, but before you go and you draw the negative direction, obviously you saw that they draw the positive direction. So knowing that we're sine, knowing that it's a sine function here, we start at 0, we go up to our amplitude and we come back down to our amplitude. All right, we come up and we go down, right? And we know that we have to repeat every 4 pi. We have to repeat every 4 pi. All right, so you can sketch that general shape. And if it's something easy like this, since you repeat every 4 pi, you know that you have to cross the 0 point at every 2 pi, right? So you go up, come back down 2 pi units later, go down, come back 2 pi units later. Same thing here, you go down 2 pi units, you go down down those 3 units, come back up and you cross at 2 pi later, up, cross at 2 pi later. Okay, so then here we can look at 2 different variations.
Times sine of 1/2 of x.
Sorry, apologies.
If you wanted to sketch the graph of y equals -3 times sine of 1/2 of x minus pi plus 5 instead, one approach would be to just flip the graph of y equals 3 times sine of 1/2 x minus pi plus 5 across the horizontal sinusoidal axis.
Okay, so hopefully you notice that here.
Sine.
Okay, so what he's saying is if you had to plot the negative of this, right, you could plot the positive direction and then just flip it across our new sinusoidal axes. All right, you could flip it across our new sinusoidal axes. That's all he did.
To just flip the graph of y equals 3 times sine of 1/2 x minus pi plus 5 across the horizontal sinusoidal axis. Here's the reason that this works. Notice that the only difference between the new function and the original is that the 3 has been replaced by a -3. The shift and period constants are the same, and the amplitude will still be 3. So the exact same reasoning will lead you to the fact that you simply need to sketch a period of minus sine with amplitude 3 in the highlighted box. Here is a period of sine. Now flip across the sinusoidal axis to get the reflected period. You can use the periodic nature of sinusoids to just repeat this shape to get the full graph.
All right.
What if instead of the original function, you were asked to sketch this function instead? The only difference is that sine has been replaced with cosine. All the shift, amplitude, and period constants are the same. So the exact same reasoning will lead you to the fact that you simply need to sketch a period of cosine in the highlighted box. Here is a period of cosine. You can use the periodic nature of sinusoids to just repeat this shape to get the full graph.
All right. So again, what he's highlighting here is that these graphs have a very repetitive nature to them, right? You can still highlight where your graph is going to exist, right? But the two major things are going to be if you have a negative value out in front, or you have a negative constant that you're multiplying by, and if it's sine or cosine, right? If it's sine or cosine, you still follow the same basic parameters here. You just have to then figure out, again, what the exact shape will look like. Okay, so then now that we know how to sketch the graph, it's asking us, can we work backwards? So if we have the graph, can we figure out what the equation is? All right, so looking at the graph of this sinusoid, obviously we know that it is going to be either sine or cosine, right? So that's the first thing that we can notice here.
Consider this graph of a sinusoid. The first step to finding its equation will be to try to find the sinusoidal axis. The horizontal component of the axis will be halfway between the maximum and the minimum of the sinusoid.
Okay, so, I guess step 0 is identifying that it is a sinusoid, it's sine or cosine, right? Then he says step 1, okay? Step 1 is identifying the max and the min, all right? So he drew that little dashed green line here, and we know that our horizontal axes has to exist halfway between them. So if we look at -1 and 5, what's halfway between them? Oh, -3. All right, so that's the horizontal axes of our sinusoid.
Since half of the distance between the maximum and the minimum is 2, you know that the amplitude must be 2, and the horizontal axis is at y equals -3. Choose the vertical sinusoidal axis at x equals 2 pi over 3.
Okay. So if we look there at 2 pi over 3, if we look at 2 pi over 3, part of the reason it looks like he chose this is because it's exactly on a value that we know, 2 pi over 3, right? If I go to pi over 3 here, if I follow this down, it doesn't land nicely on my graph. Doesn't land nicely on my graph, all right? And it's always easiest to start in the positive x direction if possible. All right, so what we can notice here is that, okay, I've got my 2 pi over 3 because it's right on there. So this is my new sinusoidal axis.
Now that you have your sinusoidal axis, you should identify one period. You can do this graphically. Remember that one period will have occurred when the function completes one full cycle.
Okay, so from 2 pi over 3 to 5 pi over 3, that is 1 pi. Okay, that's 1 pi. And how you could do that is just subtract them if you didn't know that. Or you could just subtract them if you didn't know that. Okay, so then looking at the repetitive nature, the question becomes, is it sine or cosine? Well, if it starts away from this origin point of our new axes, that makes it a cosine function. All right? This makes it a cosine. And the reason that is because normally cosine of 0 equals 1, while sine of 0 would equal 1. So again, if it was sine, it would start down here. But since it starts at a high point, it is cosine.
Here's what you know so far. Relative to the sinusoidal axis centered at the point 2 pi over 3 minus 3, you have the graph of cosine with amplitude 2 and period pi. It turns out that this is enough information to get the equation. Remember that A corresponds to the amplitude, that C and D correspond to the center of the sinusoidal axis, and that B determines the period. You can check this equation on your graphing calculator.
Okay. Another thing I want to point out too, he mentioned amplitude earlier, but we kind of glossed over it. Again, the amplitude is just the distance from our sinusoidal axes to a max or a min point. So again, from -3 to 1, a -1 is a value of 2. So that's how we got that amplitude there. All right, and again, we can just fill this in. We know that our amplitude was multiplied by 2. We know it's a cosine function. We know that it was compressed. All right, it was compressed because we had our period of pi, right? So if we know that our period is pi, we can solve for our b value by doing this 2 pi over b. B has to be equal to 2. Right, so again, filling in that equation there based on our components, right? So then looking at this here, as we know, we have many sinusoid functions that can have the same graph, right? Like if you would have picked a different axis point, you could have had a different equation. So if we look at the graph that we were just looking at here.
What you choose for the vertical component of the sinusoidal axis is up to you. Some choices determine a period that looks like the function sine, while other choices give what looks like cosine. Originally, you chose the vertical sinusoidal axis at x equals 2 pi over 3. This seemed like a good choice since it was easy to tell what the x value was.
Okay, again, that's exactly what I said, right? So they said you could have chosen any of these. You could have chosen that one there that looks like a sine function. But as you notice, if you notice that green line here doesn't match up nicely with something that we know that or something that's on this scale. So again, the reason he picked what he picked was because it was easy and it matched up nicely on our x-axis there.
Other choices give what looks like cosine. Originally, you chose the vertical sinusoidal axis at x equals 2 pi over 3. This seemed like a good choice since it was easy to tell what the x value was. What if you were to choose a different vertical sinusoidal axis? The period of this sinusoid is still pi, but now the highlighted period looks like the sine function. Thus, the equation will change drastically. Use your graphing calculator to check that this equation also gives the correct answer. It turns out that there are an infinite number of functions that have the same graph. Here are a few others.
Okay, so again, your choice is going to be very important. All right, and again, normally, if you were taking a test or if I had you taking those teacher scored tests, right, you would have potentially a bunch of different options depending on where you picked your y-axis to land for your new sinusoidal axes. All right, so just be very careful that when you're looking at multiple choice questions for your quiz and for your CST, that when you're determining the equation, if your equation isn't up there, right? If your equation isn't up there, then you should probably check some of the other options as well. Okay, check some of the other options as well, because maybe the computer or maybe Apex picked a different vertical axis than what you picked to make your equation. All right, so there's multiple equations that will result in the same graph. It just depends on what you're looking for, and that's kind of the nature of the beast with these periodic repeating graphs. All right, so then look here, choosing sine or cosine. All right, you can see that they can result in the same graph depending on if you shift them or not. All right, so looking here at the red one and the blue one, okay, looking here at the red one and the blue one, again, you can look at the conclusion that it's the same thing. So if I have sine of x plus pi over 2, right, plus pi over 2. If I shift it, it's going to look like my cosine graph. Okay, I plus pi over 2, it's going to look like cosine. If I take my cosine and I subtract pi over 2, it's going to look like my sine graph there. All right, so you can plug them in your graphing calculator or you can just take my word for it. But again, that's the nature of these repeating graphs. You can shift them to make them look like the other one. All right, and then finally here, the other trigonomic functions. Okay, so the secants, the cotangents, the tangents. All right, Some of these don't have an amplitude, or all of them, I guess, technically don't have an amplitude, okay? So when you look at A, instead of changing the amplitude, it's simply going to stretch or contract along the y-axis. All right, it's simply going to stretch or contract along the y-axis. So if we look down here.
Here is the graph of tangent. It has vertical asymptotes at odd multiples of pi over 2. Just as before, the constant A determines the vertical stretch or contraction, B determines the period, and C and D determine the shifts. Using what you know about vertical and horizontal shifts, you can calculate what shifts have taken place for this function.
Okay, so that would be, again, my new sinusoidal axes right there that they just drew in blue.
Here is the graph of tangent. It has vertical asymptotes at odd multiples of pi over 2.
Sorry, there you go.
Now calculate where the first asymptote to the left and to the right will be. This also determines the period of the function. Push the buttons for 2 ways to calculate these asymptotes.
All right, so look there. Okay, since it has this form, we have a new period, right? We have a new period, and also we know that we shifted over to the right, pi over 2, right? And we shifted up 2 units. So that's how we got our new sinusoidal axes. All right, we got our new sinusoidal axes, then we have our new period here. All right, so now we know that our new asymptotes will be at these 2 values. Okay, so this is one way of calculating this. All right, for calculation 2, you can notice that you're going to have a vertical asymptote at pi over 2 and pi over 4 since this value here. Okay, this is where it would be undefined at. All right, personally, I like looking at this version. It's a little bit easier for me, but either of these calculations work here.
Now you can sketch one period of 1/2 tangent x with period pi over 2. Keep in mind that the factor of 1/2 will dampen the growth of the function, just as a factor less than 1 in a sinusoid will decrease the amplitude. In other words, the factor of 1/2 will contract the graph along the y-axis. Now, using the periodic nature of the tangent function, you can repeat this to get the full graph.
Okay, and in tangent and cotangent, they're talking about squishing this little s. So instead of having a really large s, okay, if it's a compression, you squish the s so it's a little bit flatter. If this was a large number like 3, you would elongate that s, make it drawn out, right? Really stretch it. Okay, dealing with secant and cosecant here. Okay, so dealing with cosecant and secant. Unlike tangent and cotangent, though, secant has no zeros. Secant has no zeros, so the stretch or contraction might be a little bit more difficult, okay? So, for example, here, in particular, the vertical stretch or contraction caused by A will have what appears to be a vertical shift. But be careful that the shift is part of the stretch or contraction, because if we look at it, secant of 0 equals 1. Okay, secant of 0 is equal to 1. All right, so if I have a secant of 0, it's going to look like A. All right, thus the y value of 1 gets shifted to A. All right, so it gets shifted to A. So I know that that's confusing. So when we look at what that looks like here.
Now calculate where the asymptotes will be. This also determines the period of the function. Push the buttons for 2 ways to calculate these asymptotes.
Okay, so noticing here, sorry, that's the expression that we're working with here. 2/5 secants of this expression. So we know that we're going to move it down and to the left, so that's how we got our new axes here. All right, we know that we're multiplying by 2x, so we know that we have to divide 2 pi divided by this value here, so 2 pi divided by 2 gives us our new period of pi. Okay, so again, this is the calculation that I prefer, but if you like, you can also do this second calculation here and figure out where the values would be undefined. All right, but once you found your new axis of symmetry, you found your new asymptote lines or the periods, okay, you can then draw.
Now you can sketch one period of 2/5 secant with period pi. Keep in mind that the factor of 2/5 will dampen the growth of the function, just as a factor less than 1 in a sinusoid will decrease the amplitude. In other words, the factor of 2/5 will contract the graph along the y-axis. Now, using the periodic nature of the secant function, you can repeat this to get the full graph.
All right, 2/5, right? It goes down to the 2/5. All right, and again, being careful that normally it would be at 1, so it looks like it's shifted down, but since it's outside, right, it's really that multiplication, right? It's really that multiplication.
Another way to sketch this graph is to start with a corresponding cosine graph. Ignoring the vertical shift down 1 unit, here's a sketch of the two together. Focusing on one period, you can see how the reciprocal relationship looks graphically. Note how the 5/2 becomes the 2/5, and the 0 becomes undefined.
Right, so that's another way of looking at it too. Okay, so that's what they're saying. You can flip, vertical shift. All right. So for the sake of time here, I'm going to let you go over the review questions, and I'm going to let you look at the study guide. We'll just gloss through it quickly because we got about 8 minutes left in class here. All right. So again, these are still doing the shifts and compressions, but it's putting it all together and understanding what that means. Right, understanding what that means. And the big key here, that's why we're dealing with these functions, is finding that new sinusoidal axes. All right, finding that new sinusoidal axes is going to be very, very important. Okay, because once you find that axis, the rest of the information is hopefully pretty easy here. And that's just the beauty of these repeating graphs. All right, that's just the beauty of these repeating graphs here. All right, so in 2.4, you have this quiz here. So again, to remind you of what kind of your assignments are to complete by Monday. All right, you need to do this 2.3 quiz, do this 2.4 quiz, and then obviously you need to come and wrap this unit up once you feel confident. Okay, once you feel confident. All right, and again, I would suggest really going through these reviews, especially those calculator skills, because your calculator should be your new best friend in trig. Should be your new best friend if you weren't already good friends there. All right. So you'll do the review, you can do the practice or the discussion for extra credit, and again, you can get partial extra credit if you'd like, right? Just do some of it and turn it in, okay? And then you're required to do your CST, only the CST here. All right,